Hello and welcome to the 7th tutorial for the program Solfem v3. In this tutorial we are going to create a hex mesh, and we are also going to create a dummy mass element which we will attach to the hex mesh using a spider. So let's get started. We'll open up a new terminal window and navigate to the Solfem work directory. And start up the Python script program.py and select the viewer. Here we go. Now we will create this hex mesh from scratch, and so we need to first create an empty mesh. There we go. And to start we will create a hex 8 element, and we'll make it let's make it 2 millimeters. The sides let's make the sides 2 millimeters. So there we go. And to start, let's just extrude it. Let's start with 12 elements. And then we can select all the elements again and extrude it in the Y direction. And let's extrude it 6. Okay. Now this is going to be a plate, and I kind of want, let's see, there's the origin down there. Click the origin button. I want this plate to have these well, I will show you. Let's extrude this outward in the Z direction. Let's extrude 2 elements like that. Now we can click the shaded button up here, so it's easier to see what we're making. And I'm gonna extrude. Let's try to make it look a little bit more interesting. So we can try how about 20 degrees, and we are extruding in the Y direction. We can extrude, let's say 6 elements, 60 radius of 60 here. Well, let's actually 8. Let's try 8. If we get it, if it looks bad, we can delete the elements we extrude and try again. So the axis about which we are, the angle is being extruded, will be this x-axis now. Okay. see the elements they look a little bit long here, so I think we'll try again. We'll delete the elements. Oh, we didn't get that one. And now let's try again. So that's in the Y direction. And we extruded 8, I think. But if we decrease the angle to 15, and we're extruding about the x-axis, rotating the angle about the x-axis there. Yeah, that looks good. I like that. So now we can extrude this a little bit, and actually I don't want it there. I'm just gonna delete those and extrude these. Yeah, I'll extrude these in the Z direction too. Okay, and now I have to make sure, because now I extruded new elements here, so they are not attached to the these elements next to them. So I'll just select all nodes in this area and click the Fuse Nodes button, and that'll make it so that any nodes that are on top of each other are now combined, and excessive or extra elements are just removed, deleting nodes, as you can see down here. Okay, I like this better. And finally, then I will extrude this one. Now this one is in the X direction. We'll put a little bit of an angle on this one as well. So we use the same as before, 15, and we're extruding about the y-axis, but we wanted to rotate inwards, so we have to go in the negative y-axis there, and that does it, I think. Yeah, I like this. So it's just to make it a little bit more interesting. I put a small angle on it there. I mean, it's so small it doesn't matter, but now you know how to do it. So maybe you want to create something more complicated. And as you can see here, we have the Z y-axis and the y Z plane and the x Z plane, and we can select all the elements and then click the Mirror Elements button. So let's mirror about y z, and then select all of these elements and mirror again about the xz plane. Okay. Now I just copied a lot of elements, and so these copied elements are not, they don't share the nodes with the original elements. So we again have to fuse nodes here so that the elements are connected. And there we go. Our hex mesh is ready. It's a plate here, and we're going to create a dummy mass element on this, and eventually we'll start up a modal dynamic solution. But first we have to finish creating the mesh. So let's see. We're going to select some of the nodes here on the surface of the hex mesh, and create a node set. So this will be node set number 1, and then we will copy these nodes, and we will copy them in the so that's the negative set direction, or we'll copy them with an offset vector here. And now we have to click this nodes button so that we can see individual nodes. Here we go. Excellent. And we select these copied nodes and create a new node set for them. This will be node set number 2. And then we can select one of these nodes and make sure we only selected that one, and copy this node. We'll offset this one also by -1 in the Z direction. And finally, first this will be one of the nodes in the dummy mass element. So let's give that one a node set number, node set number 3, and copy it with an offset of -1 in the Z direction. So now we have 2 nodes here, and they will be our they will make up our dummy element. We're going to use a beam element for this, and if you see, the distance between them is 1, so we're going to create a beam with length 1 and area 1, so that the volume is exactly 1. This will make it easy to write in the mass. Now select this node, and remember, this is node set number 3 and these are node set number 2. So with this node selected, click the spider button, and it asks what node set you want to create the spider from, and then you select these nodes. That's node set number 2. So what just happened is now it created a set of beam elements which are unnaturally stiff. So they will attach this dummy mass element to the hex mesh down here, and actually we're going to select node set number 2 again and move it down so that it's almost on top of the hex mesh. So we'll move nodes, and if you remember, it was offset -1 in the Z direction, so we'll move it 0.9, and there we go. Now we'll select these two and create a beam element. So the easiest way to do that is to just click insert elements when you have 2 nodes selected. So insert, and there we go. We have our dummy beam element. And actually let's just now we have it selected, we can just give it an element set number. We'll call this one element set number 2 actually, and let's select all of the hex elements. Make sure we didn't select any of the spider elements there. Nope. So that's good. And we'll give the hex elements element set number 1. Excellent. That means we have all our elements. Now we need to give them properties. So we are going to create this dummy mass element, and then we need a dummy mass material, and we will call it dummy mass. And for elasticity, let's just make it unnaturally stiff. I think that is the stiffness of the spider elements. So and 0.3 there. Now, since we give it volume 1, that means here this will be density is kilograms per square millimeters. So no, cubic millimeters, sorry. So here we can just type in now the mass that we want in kilograms. So let's give it a mass of 0.1 kilograms, so that's 100 grams. That may be a bit much. We can check here the distance between these nodes, 82, so that's 8 centimeters, about 100. It's okay. Well, if it's very unrealistic, we're just making something here just to show how the program works. So now we have the material. We will create a section. So we'll call this dummy section and use dummy mass for that. Don't use this one. This is for the spider elements. This was automatically created and applied. So, and well, this one will be 1, and these the easiest way to do this is to just leave these as they are now and click this button, modify beam section. So we will modify our dummy section. Make sure you're not doing anything to this one. Dummy section, and select a rectangular cross section. And if you set the inner width and inner height to 0, that will make it solid, so it's not a hollow rectangular cross section. So here we have the area 1 and this moment of area calculated. So that's good. Now we have apply the dummy section to element set number 2 there. Yeah. So now we have the dummy element with section properties. So as you can see here now, sections still not applied. This means there are elements in our mesh that do not have section properties. Of course, our hex mesh. And so we create a new section, and let's just use aluminum in newtons, millimeters, and kilograms. And this is a 3D hex mesh, so you don't need any of these properties for this section. And apply section, that's section 1 there, to element set number 1. And now we have section properties on all our elements, so we are ready to create solutions. And let's start with an eigenmodes solution to see that everything is connected. We need to select nodes for our boundary conditions. So we're going to use these here. These will be we'll just pretend like they are where the part is bolted to whatever structure our part is fastened to. So we'll just create node set number 4 from these. And if we click this button, current solution, we can see our solution, this one here. And now apply boundary conditions to the new node set. All degrees of freedom, well, actually they only have the 3 first one here, and 0 displacement. So now you can see boundary conditions were applied, and we need to create the multipoint constraint between the spider and the hex elements, because the spider consists of beam elements, so these have 6 degrees of freedom, but the nodes in the hex elements only have 3 degrees of freedom. So we need to lock these 3 degrees of freedom in the 2 node sets there. And the distance between the nodes was exactly 0.1. So let's just set it a little bit higher, and the tolerance, I mean. So that does it. And there you can see we have a touch lock constraint. So if you mess up or if you get the tolerance wrong between these nodes, the solver will crash when you try to run the solution, and so you might have to go into the solution file, the text file, and adjust this a little bit sometimes. In this case, you can set the tolerance too high. So too high in this case would be 1, because there's a distance of 1 between neighboring nodes, and if you only want these two nodes to be within the tolerance of each other. Otherwise, the multipoint constraints will the solver will try to create several multipoint constraints on the same node, and that will crash the solver. So keep that in mind if you are applying multipoint constraints yourself. So we have now boundary conditions and a touch lock constraint here, and section properties on everything. So we are ready to run an eigenmodes solution to see that everything is connected. So that's solution. Let's call it solution file 1, and just 8 mode shapes is enough. We're just trying to see that it works. Okay, so solution file 1 written here, and we can run it in the solver. We'll select solution file 1 there, and it is running, and it is finished. So we can now open solution file 1 out file and have a look at mode shape number 1. And there we go. The dummy mass is dominating this first eigenmode. That's 32 Hertz. Everything looks like it's connected. It's yeah, everything is happening in this area. And here we have some more. It might have been more realistic if we locked the nodes, not just the surface nodes here, but all the way to the surface. But anyway, this second mode also very dominated by movement of the dummy mass. And the third mode, same. Yeah, it's I mean, it's not super realistic here, but it's just an example where we can try out how the program works. So yeah, I think it looks like the first 5 modes there are the important ones. Here you can see the frequencies are very high. So, and the last one even higher. Yeah. So the first 5 modes seem to be the most important, and now we need, before we start working on a modal dynamic solution, we need to have input in the form of acceleration over time. And what we can do here, just to create an example, we can use this generator.py script. It's in the Solfem v3 work directory. So this one was used to create the input in tutorial 11. You can see up here there are tutorials. Tutorial 11 is a tutorial for a modal dynamic solution, and we can just modify it a little bit, maybe. Instead of 12 seconds, we can set it to 6. We can cut off there. Cut off at 4 seconds, maybe. So this is these are just numpy or is it a vector? Well, yeah, I think so. NumPy vectors. And so this is a sinusoidal wave with a frequency 1.7. Our first eigenfrequency was 30 something. Let's set this one to 29. See if that comes close enough to trigger anything. And let's just make it a little bit more interesting than just a sine wave. We can add a cosine wave there, and another sine wave maybe. Let's say 3. 49. And let's also give it the name tutorial 7 base motion.tab. This will be the file name we need to specify in the solution file. So we save that and we open another terminal window, navigate to the Solfem work directory and run the script generator.py. So this is the input. It's not very realistic, obviously, but it will work as our example. So here you can see it. We can have a look at it actually, just to see, so you see what the format is. So on the left here are the amplitudes, and on the right here are the time steps. So you need to, if you are using data, real world data, something you have measured, and the time steps are not the same, then you need to pre-process your data so that your tab file is in this format. It can be like a different time step, but it has to be the same delta t for the next one. So it's pretty simple, but you know, this is not meant to be like a replacement for commercial software exactly. It's more like quick and dirty calculations, and also something you can run on your home computer without having to buy an expensive license. So now that we have that input, we have loaded results here. So we need to clear out before we start creating our Modal Dynamic solution. We need to clear out the viewer so that there's no chance of overlap between the results and the new the mesh we are working on. This is it happens sometimes, so it's just easiest to just clear out the viewer, and then we can import solution file 1. That's the one we created. So here it is. You can click the shaded button there, and now let's create a Modal Dynamic solution. We'll just call that solution 2, and we will show that as the current solution. Now it needs the same boundary conditions, so that was node set number 4. Make sure it's solution 2 here. We can see that they were applied. Excellent. And the same multipoint constraints there. So that was node sets 1 and 2 with a tolerance of 0.15, and here it's actually important that you write in only these degrees of freedom, because if it tries to lock rotational degrees of freedom and the hex elements do not have these, I think maybe the solver will crash, so keep that in mind. And this is ready. Now we are going to create a dynamic load, and this load on solution 2, that's important. This load, we will create a acceleration load type here. This means it's a acceleration of the base motion, so it's accelerating the nodes at the boundary condition, at 0 displacement boundary conditions. So this one, force dynamic, this is different. Here it's not using the boundary conditions to apply the load. Here you have to set boundary conditions somewhere else and then apply this as a dynamic force being applied to the structure, so that it's being held back with 0 displacement at the boundaries, and wherever you are applying the force is pushing on the structure. But for this tutorial, let's use base acceleration. And also the solver is written, it's not great. This is fairly slow, base acceleration. It's because of how the solver is written. It needs to be rewritten. This is fast, as you would expect from a modal dynamic solution. So anyway, let's start with, now let's select acceleration here, and we are applying it to the nodes, same as the boundary condition there. We can yeah, let's just keep this, and we're applying it in the, should we apply it in the Z direction, or, well, I mean, we can apply it like this, so in the ZY direction. Yeah, let's do that. See how that goes. And here you can see the load is applied there to the boundary conditions in that direction. So then we have everything we need here, and we can create the solution file. So let's call it solution file 2. Now we don't need solution 1. We already looked at that one. So let's just add solution 2, and we want to see the displacements at the dummy mass element. So that's node set number 3. Let's also look at the accelerations there, and let's ask for results in text format as well as PLT. That means you get results you can open in the viewer, same as stress plots and displacement plots. Yeah. And here the damping ratio, we can use damping ratio that changes by frequency, so that it becomes higher with the higher frequencies, but let's just use 0.02 here. And now we have to write in the file name of the input here, tutorial 7 base motion, and let's just do that. Tutorial 7 base motion dot tab. So that's solution file 2 there. You can have a look at it and see if there's anything interesting. Actually, yeah, let's no, let's not do that. Well, yeah, let's do that. No, sorry. These are the, yeah, here you can see the section properties of unobtainium. This is what is being used in the spider elements, and here the dummy mass element. So these are much higher than the stiffness in the hex elements. This can become a problem. So if you get weird results, you might want to just reduce this stiffness. You can actually see an example of that in tutorial number, I think it's tutorial number 9, where you see the results are it's difficult. I can't really zoom in here, but you get kind of I don't know if it's a singularity, but the spider elements are too stiff compared to the TET4 elements here, so that it deforms the mesh where it shouldn't. But if you then go in, this is tutorial 9 in the example mesh tutorials. if you just went in then and reduced the stiffness of the spider elements a little bit, it removed that unwanted deformation there. So that's good to know if you are having problems with the spider. And boundary, yeah, constraint, load, and here we see the tab file that we created is referenced here. And yeah, it's pretty straightforward. This is the damping ratio. Now if we were using damping ratio changing by frequency, we would need a tab file with that, and you can see an example of that again in tutorial 11 here. So this looks good. We can now run solution file 2 with our Modal Dynamics solution. And this one is probably going to be a bit slow because it's base acceleration, and so I'll just go in and edit the video here so you don't have to wait for the solver. Alright, we have our solution finished there. You can see the solution time was 124 seconds, so that's 2 minutes. That's a lot more than you would expect from a Modal Dynamics solution of just 9,888 degrees of freedom. But yeah, so keep that in mind if you want to use the base motion on the Modal Dynamics solution. It will be pretty slow for large models. And so the solution, that's the solution file 2. It created a results file there, an out file with the results we can open in the viewer, and the same the results in a CSV file, which we can have a look at that after we first open the solution file 2 out file. Now here we have new results available, displacements and acceleration. So acceleration, just node 0 here. If it's base motion, it includes node 0. That's just so you can see the accelerations, the input. So I don't know if we can see the difference. It was in the Z and Y direction, so I guess they're overlapping, and in the X direction it's 0. So that's node 0. That's the same as we saw when we generated the tab file. And at node 3488, that's the dummy element. Here we can see the response in all 6 degrees of freedom. Now I mean the input acceleration was about 20, so this is 60. I mean there is definitely and increase there. The acceleration is 3 times higher at the dummy mass element, but it doesn't look like we have any serious resonance really. It's being accelerated, and then when the acceleration stops, it just dampens out there. And we would expect the Z and Y direction to be well, yeah, that makes sense. The Z direction is being accelerated more. If you remember the eigenmode 1 was close to 30 hertz. Oh, and that was moving in the Z direction there, so that makes sense. And we can also look at the relative displacements here. So this will be displacements because this is base acceleration. Then the displacements will be relative to base. So here we can see how much deformation we're talking about, and that's much less than a millimeter, so guess that's not so bad. Yeah, so now you know how that works, and we can also, let's open up the CSV file just to have a look. Now you can use I mean, if you prefer a spreadsheet, you can load the CSV file in there. I like to use the Python module pandas for this. So if you don't have pandas installed, I think on Ubuntu that's sudo apt install python 3 pandas. This will install that module for you. On Windows you will use pip install pandas. I think I might be wrong. It's the same as the way you installed all the other modules when you installed Solfem. So yeah, now let's just open up a Python, and or we'll start up Python and import pandas as PD and import matplotlib.pyplot as PLT, and we will create a variable. Let's call it df for data frame, and we will import the CSV file data into this variable. So it's pd read csv, and the name of our file, that's solfile2.sol, and it did not want to do that. No, of course not. That's sol.csv. There we go. Now we can type df head. That's a function to look at the data, just to get an idea of what it looks like. And yeah, it loaded the data. So now type plt plot df time there, and if this is going a bit fast, then just pause the video. Acceleration node 0, and let's have the Z direction there. And what was the node number at the dummy mass? That's 3488. So 3488, and then PLT show. Then we can compare the two accelerations there. Zoom in. So the blue one is then the acceleration in the Z direction at the base, and this is the acceleration at the dummy mass element. So that's this is just to show you that you can, if you want to post-process the results from the CSV file yourself, you can do that. So that does it for this tutorial number 7. You now know how to create a new hex mesh, and of course, should you want to use different elements, sometimes you just need to use tet elements, because these elements are not, there's no hourglass control here, so if yeah, some for some types of meshes, then these hex elements will not, they just won't work. But then you can always select your elements and convert them to tet elements, and they always work. They just there are more nodes, so the solution will be slower, but it will work. And you also learned how to create a spider and attach it to your hex, or same procedure for tet elements. And you also learned how to create a dummy mass element. So I hope you found this useful, and thank you for watching. Have fun.